Lecture 9.8, Analyzing and Interpreting the Magnetic Field of a Circular Loop. So there's probably about 4 or 5 points that I want to make in interpreting this field. The first one is the circular loop magnetic field leads to two useful field equations. One, the most important one is the circular coil with N turns. So if I look at that magnetic field, it looks something like this. I'm going to have B of an N turn coil is then going to be the number of turns times the magnetic field of a loop, where in this case, the arc length is then going to be 2 pi r. And this leads to a relationship that reads 2 times r squared z squared to the 3/2. And this is all going to be divided into mu naught ni r squared. So this right here is the magnetic field of a coil with N turns. Now, if you look at this field, we've already shown an image of this, but it's worth looking at again. You could see that this coil has N turns and it produces a magnetic field when it has a current running through that coil. So without a doubt, this is the most useful relationship. Another one that's used a lot in physics here is that if you have a single loop with an arbitrary arc length. Now, if you write this out, just to remind you, the arc length is r times theta. We can then say that this is then going to be the magnetic field of a single loop. But typically, I just write this as B loop. And when you write this out, it reads like this: 4 pi r squared z squared to the 3/2. All of this goes into mu naught I r. And then I multiply this by, of course, the arc length. Now, if we analyze these two fields, here's sort of like my interpretation of what is going on. The field of a coil with N turns is most useful for many problems because it continues to show up. So for many problems in this and the next chapter. Now, I should be careful here is that it's not only the coil of a circular coil that is, but there's also the solenoid. Both of those is what shows up the most. The single loop field is less useful. What do I mean by less useful? It shows up not very much in real problems, but it is instructive in teaching the direction of the magnetic field in uncommon situations. Now, I want to be careful because it may come back and bite me in the ass by saying that, but that's what I remember. Excuse me. So here's a textbook type problem. So here is a textbook type of, I guess, application of a single loop field. And really what we're going to be asking here is because we're focusing on understanding the direction of the magnetic field is we're going to ask, what is the magnetic field at the center of curvature? And in my opinion, I just really think about this as just being the origin that we have defined. So let me try to draw this. So there's many situations. And one that I could do here is that I imagine that I have an arc. And I'm going to need some reference. So I'm going to draw my second arc here. So these will not be pretty. But you could imagine that I have a single coil, excuse me, a single loop configuration that looks something like this. So here's my configuration. So this is really a single wire. And what you can see here is that there are two different radii. So the center of curvature or the origin, I'm going to call this R1. And I'm going to call this guy R2. Now note that these are infinitely thin. But what I really want to look at is that I want to look at the current. So what is the current? Let's just pick an arbitrary current. Let's say that I pick this current to go this way, which then means it goes in that direction, which then means that it goes this way, And of course, we can just follow this guy all the way around, where these are the currents here. So we can see here is that there's segments to this coil. So actually, I'm going to move this eye and I'm going to put it right here. So I'm going to say that this segment right here is going to be segment number 1. I could have picked any direction that I wanted. This will be segment number 2, segment number 3, and this will be segment number 4. So we see here is that there are 4 segments. There are 4 wire segments, and we see here is that 2 are straight wires and 2 are curved wires. Let's compute the magnetic field for each wire segment. So we should define a coordinate system. So one of my favorites here is to call this X, Y, and then this will then be Z. So I have a segment of 1, 2, 3, and 4. So I'm going to call those points 1, 2, 3, and 4. So here we go. So I'm going to focus on point 1. So what do I see about point 1? Well, look at 1. Everything's measured relative to the origin. So you can clearly see that we have a current moving like this for current 1. And when I look at the my vector, my displacement vector, you can see that the displacement vector is in the same direction as the wire, so therefore its magnetic field must be 0. So if I pick out point 3 because it's the exact same type of scenario here, then we just reverse it here. We have a current here at 3. You know, I shouldn't even be labeling 1 and 3. And you could see that in this situation, R is in the opposite direction. So this will then give me a magnetic field of 0. Now let's look at point 2. Now we're going to look at the curved parts. Well, when you look at 2, note that this is a smaller loop compared to the bigger loop. So if I'm closer to O, the magnetic field has to be stronger. If I'm at, the wire segment 4, that magnetic field has to be weaker because it's farther away. So when I start drawing this, what am I actually seeing? So I have a small curve right here. Let's say that this is my curve. And of course, this is a relative curve. And what I'm interested in here is that I'm interested in, if I'm going to measure everything from here, then I'm going to see that this is going to be at point P. Here's my direction of R. Actually, I should call that big R, since that's what I labeled it earlier. And then the current is going like this at this particular point. So when I look at this thing, we can clearly see that the magnetic field right in here should be quite large for 2 because the distance is small. So if I compare that to point 4, well, that loop is larger. So if it's larger, we're really talking about something like this. And I could probably move this a little bit closer up here. And as I look at that, at the very top, we can see that the current is going to the left. And note that I'm only picking one point. So if I pick a point here, let's say up at the top here, that's the direction of my current. You can now see that at this point P here, my displacement vector, R4, note that I labeled this 1, but it should be 2. R4 is big. And because it's big, that means it's farther away. That magnetic field should be smaller at 4. So now if I apply superposition to this, we can then say that the net field at point P via superposition is, I have a magnetic field, B net, and it has a direction, and I'm going to get B1 plus B2 plus B3 plus B4. So I have 4 vectors like this. And what we're finding here is that we know that the magnetic field of 1 is 0. We know that 3 is 0. So now note that Z is positive coming out of the page, but we're seeing that the bigger field is negative going into the page. So then, because they're half arcs, then we're going to say that we have this. So I have 4 pi, and I'm going to have R1 squared plus 0 to the 3 halves divided into mu naught I R1, but then I have to worry about the arc length, right? We got to use that relationship with the arc length, and since this is half a circle, this should be R1 pi minus, oh, this should be minus, and this should be plus. So then I should have 4 pi R2 squared plus 0 squared to the 3 halves. And this will be mu naught I R2, and this will also be R2 pi. And of course, this is going to be in the Z direction. So if I clean this up, what do I actually find here? I find that the magnetic field here should be mu naught I divided by 4 times the quantity 1 minus R1, 1 minus R2 in the Z direction. And of course, I have to put a minus sign out here. And this is going to be the net magnetic field. So this is why that relationship is useful. We could just use it to just pick off those values. Another relationship that we should think about in some detail here is the factor of N in the magnetic field of a coil is the reason why coils and not single loops are used to produce strong magnetic fields. To obtain, I guess, desired field strengths, assuming that the field is high enough, a single loop would require a large enough current that it will most likely exceed the rating of amps of the wire. So let's look at an example. And you can see what I'm talking about. So when you look at household wiring, it typically uses 14 gauge wires that could handle 15 to 20 amps. So we're saying that a 14 gauge wire can handle 15 to 20 amps. If you exceed that, you're going to run into problems. So suppose a single loop and a coil of 5,000 turns. So why do I pick 5,000 turns? Because we have probably 16 in our lab. So we have a coil of 5,000 turns that has a radius of 10 centimeters, where each produces a magnetic field of strength 0.5 Tesla. That's a strong magnetic field. So here's our question. To give you a sense of why a single loop is bad versus a coil, what we want to do here is that we're asking the question, what current is required to induce such a strong magnetic field of 0.5 Tesla. So let's look at this. So we have a general relationship that we'll use, and we'll say here is that the magnetic field at the center, which means Z equals to 0, is then going to read like this. So the magnetic field of Z equals to 0 is then going to be 4 pi r squared plus 0 squared to the 3 halves. And then I'm going to get mu naught I n r, where for a full circle it's going to be 2 pi r, which then leads to a relationship of mu naught I times n divided by 2r. So now we want to look at two situations. So for a single loop, that means n is equal to 1. And we find here is that the magnetic field of a loop is then going to read, no, I should be careful and say that this is right at the middle of the coil, is then going to be mu naught I divided by 2r. So now if I now solve for the current, I'm going to get that the current of a single loop then has to be 2r times b divided by mu naught. So let's put in the values that we talked about. So the values are that I'm going to have 2. What's the radius of this thing? It's going to be 10 times 10 to the minus 2 meters times a magnetic field of 0.5 Tesla divided by this constant, which is 4 pi times 10 to the minus 7 newtons times divided by amp squared. And you get a value that reads 40,000 amps. That's a lot of current. That's kind of the current that's produced by power plants. That's a huge current. Now let's go look at N-turn. An N-turn coil. And in this situation, because we have these in the lab, they have 5,000 turns. So if I repeat the same process for this guy, here's what we're going to find. We're going to find that the current of an N-turn coil is going to be exactly of what we calculated before. This is going to be the current of a loop, but now I have what? I have a whole bunch of loops. So this tells me here is that I'm going to get 40,000 amps divided by 5,000 turns, which then means each loop gets 8 amps. So if you look at this thing, if you put a 14 gauge wire and you ran 40,000 amps to it, this is going to burn up explosively. This one is going to be no problem at all. So you could see why an N-turn coil is much more important than a single one. Okay, so let's go to the third thing that the second thing that I wanted to say. Right, I think this is the second. I don't know what my numbering is. Nope, that's 2. So this should be 3. So let's plot the magnetic field of a coil of n turns, of course. So if I start to draw this, here's what I'm seeing. So I imagine that I have a ring, and let's say that it's this big. Now note that this guy has multiple turns. So when I'm looking right here at the middle, you could imagine that I have n turns of wire right here. So if I look at the magnetic field, I'm going to find that my magnetic field is going to look something like this here. So if I go around like this, then I'm going to see that this guy's going to start to loop around. And if I do the same thing here, this is going to loop around like that. So then if I look at the middle of this thing, my magnetic field should be going like this. And of course, the right is the north. But then we start to look at the field. And if I start to look at the field, we're seeing that the field, from what I'm trying to draw here, you're seeing that the line density in the middle, well, I drew them pretty symmetrically. I should draw them a little bit tighter. I should probably draw some more, but I'm not. So I should have a strong field here because the line density is going to be higher. And then out here, I'm going to have a weak field. So our graph should show that. So here we go. So let's see if I can scale this guy. So we know that the coil, we know what the field looks like, and it should be looking symmetric. So I'm going to say that it's going to look something like this. And I'm going to say that this guy is going to look something like this. So then my magnetic field strength, you could see that it's dropping off. Right? So there's my magnetic field. So we need to be careful how we start to write this magnetic field. So what do we know about this magnetic field? Well, if this is a coil, this is the magnetic field. And of course, this has to be 4 pi r squared z squared to the 3/2. And then this guy is going to be mu naught I r. And if it's a full coil, it's going to look something like that. So if I have that, then I'm going to see that at this point here, that guy is B max, but that max is at z equal to 0. And again, we're plotting z here. And if you look at z equal to 0, it actually simplifies to a relationship that we just saw, which will then be I times n divided by r. Now, if you were to look at the details of this thing, is that at half the value of this magnetic field, let's say that this is the half value right here, this occurs at z equal to r, the radius of the coil. And at this point, at Z equals to R, you actually get 1/2 B max, which would then, of course, be mu naught I times N divided by 2R. So there's the field. Now, let's continue to plot this because we've had a couple of things that we've been talking about. So let's see if we could summarize this. I believe this is 4. So the long distance behavior, that typically means that Z is going to be much larger than R of a coil is then going to look something like this. So if I look at this, I'm going to have Z is much, much bigger than R. I'm going to have B coil. And we know here that there's a constant that comes out. And then I'm looking at the limit as Z is getting much bigger than R of this quantity to the 3/2. So if I put this all in, we're going to see here is that I can approximate this thing to mu naught I times N R squared over 2Z cubed. So this is proportional to 1 over Z cubed. So now let's summarize what we know. So let's summarize all of the magnetic fields we currently know. So here's what we find. I have a finite wire. So if you look at the field of a finite wire, it looks like this. Mathematically, it reads Z squared L squared to the 1/2. And this will then be mu naught times 2L. And if I look at the long distance behavior, this then becomes Z of Z squared, let's say, plus 1 to the 1/2, where I'm just setting the length equal to 1 just to simplify this. And this is going to be the field of a finite wire carrying current. So now, if I look at an infinite field, we've already seen here is that this will then be 4 pi Z divided into mu naught times 2L, and we can see that we get that from up above. And this field behaves as 1 over Z, and this is our infinite wire. And that just means that L is much, much bigger than Z. And now we have the 2 parallel wires. So if you look at these wires, we then have that this will be mu naught ID divided by pi Z squared. So if I look at this field, they fall off faster than a single wire. So these are parallel wires with opposite currents. And then finally, we add the coil. So if I look at the coil, it's 2 times R squared z squared to the 3/2. And then I'm going to get an expression that reads mu naught I times n times r squared. So when I look at the long distance behavior, this behaves as 1 over z cubed. And this is for a circular coil. So this summarizes all of the magnetic fields that we know up to this point. So what does the plot look like? So if I look at the plot, I'm going to draw this. Let's see, let's try to make a big curve. Hopefully I don't have to redraw this again, but let's say that that's the size of the curve. And so what am I actually seeing? The thing that really sticks into my mind here is a finite wire and an infinite wire effectively have the same behavior except in the middle. So let's start with those. So I'm going to start off with the magnetic field of a finite wire. And I'm going to say that it's going to look something like this. Oops, I don't like that. Let me try that one more time. I want to do something like this. So then if I look at an infinite wire, the infinite wire matches initially, and then it separates in the middle, and then it matches up later on. So what I'm saying here is that if I look at this guy, this is going to be for an infinite wire. The green here is then going to be, how about if we do it like this? This will be the magnetic field of a finite wire. What we're seeing here is that the field of two infinite wires has to die off faster, right? Because that guy is effectively going to go as z squared. This goes as z. So this guy has to match up initially, or no, at the end with the finite wire. So when I draw the two wires here, it should go faster to infinity. So I'm assuming that this guy's going to be out like this, but then it should match up with the green wire at some point. And so this guy is the magnetic field of two wires with opposite currents. Now, we just looked at the coil, and the coil is somewhat symmetric. So in this situation, the field is definitely going to be much smaller than infinity. So I imagine that the peak is finite, and then the peak is then going to effectively go like this. So the red right here is then going to be the magnetic field of a circular coil. So I would say that that is a rough explanation of a plot of the magnetic field. So before we move on, there's one thing that I want to at least allude to a little bit because we're going to see these in the lab quite a bit. A Helmholtz coil has a particular configuration that produces an approximate uniform magnetic field over a small region. The size of the coils will determine how uniform it really is. So here's what we have to do. So we start with a pair of identical coils, and they're circular, that carry current. Now, how they carry current becomes important. So if they carry the same currents, that's what's called a Helmholtz coil. If they carry the opposite currents, then it's called an anti-Helmholtz coil. So we start with a pair of identical coils that carry the same currents, superposition of these two fields add together to produce a net field. So here's the setup here. So if I look at the setup, I imagine that I have something like this. I have two coils. Let's say that these are my coils. In fact, I think I'm going to make them four like this here. And then I'm going to have another coil. Oops. Right here. So what I'm seeing here is that there's a number that's important. So the number here is that, note that the radius of each of these coils, I'm going to define as R, but look at the separation from the centers. The separation from the centers is also 2 squares. So their centers are separated by the radius. So again, these are coils that have current running through them. Now I can draw these, but I found images of a website which I've linked, and here's what I find. Okay. If they have the same currents, so if they have the same currents, this is defined as a Helmholtz coil. And we use these in the lab quite a bit. And what you're seeing here is that this is the magnetic field here. So let me make this a little bit smaller. So this green one right here is the magnetic field of the green coil listed up above. And then the second coil, the blue coil, also produces a magnetic field that looks like this. So if I look at this, I'm going to say that this is the magnetic field of, let's say, the green coil. This is the magnetic field of the blue coil. But now look at the red. The red here is the superposition of these two fields. Now note that it says normalize it, so it actually skews it a little bit, but this says that the net field is then going to be a combination of the green coil plus the blue coil. That's how I get this magnetic field. What happens if you change the directions of the coils? So by the way, I should say that typically the magnetic field is not this flat unless you have really big coils. But in our lab, we don't. Excuse me. So now let's look at opposite currents. So if I look at opposite currents, this is what's called the anti-Helmholtz coil. And so one of these is just reversed. Okay, one of these is just reversed. So I'm going to have to adjust this image right here to match it up to what I have right here. So let me look at this guy here, and I'm going to say, I'm going to try to put it roughly on the same scale here. So what I'm seeing here is that now, look at the green coil. So the green coil does not change its direction. What does change the direction is the current of the blue coil. So this is the green coil, excuse me. And then over here, this is the blue coil. And what you're seeing here is that the red right here is a superposition of these two coils right here. So right here, when I look at B net, because of the sign difference, I'm getting a minus sign between them. So then this is the B coil, and this is the blue coil, but you're seeing that there's a subtraction. We have experiments that actually do a pretty good job of measuring these magnetic fields, and they actually look like this. So as an image that I want to show you here, here are two coils that I want to share. This guy right here has a large number of turns. This has a small number of turns. And so if I look at the large number of turns, you're going to get this flat spot much better. But typically, it's not that flat for the low number of turns.